Hello everyone, my name is Shahzad and today I am presenting our paper titled Flexible Path Programming Framework for Large-Scale IoT. This paper was submitted to the NEAC workshop of CCGrid Conference 2020. This is the outline of our presentation. First, we will go through the introduction section in which we will briefly present our problem statement and our proposal, and then we will briefly touch the SDN architecture because that is the base technology that we have used to develop our framework. Then we will see the overall architecture of our framework design, and then we will come to the user syntax that we have developed to enable the user to send user-defined commands to the framework. Then we have our main algorithm that we have developed for flexible IoT data path installation, and then we will cover the experimental evaluation of our system with some baseline, and last but not the least, we will see the conclusion of our presentation. The problem statement. With the rapid increase in smart objects forming IoT fabric, it is likely to see millions of devices connected to the internet forming large-scale IoT networks. This expeditious increase in IoT devices is giving rise to increased user requirements and network complexity. With the tremendous numbers of IoT devices and users connected, there come some challenges like data collection with simplicity and optimal network utilization, the bottleneck issue that we have towards the cloud when we are moving towards the cloud or the server. In this work, we propose efficient fog layer processing and routing of IoT data using SDN, software-defined networking, and DPI, deep packet inspection. This will reduce the amount of data arriving at servers, clouds, and subsequently making it possible to cope with massive IoT data processing while meeting each user requirements. We have used SDN as our base technology to develop Flip. So in this slide, we give a brief overview of what SDN is. So SDN is basically the separation of control plane and data plane. In a traditional network, the control entity is at the same point as the data plane, is lying in the data plane here. But in SDN, we separate the control plane from each of the forwarding devices and move it to a central location. It can be a distributed location as well. But here in this diagram, you can see the network operating system is acting at the control plane and making all the decisions, while the devices in the data plane are just forwarding devices that receive instructions from the control plane and forward the packets as instructed. These days, we also have programmable data planes. For example, we have P4 switches now, which user can program themselves. And on top of the control plane, we have the application plane, on which we have some well-defined APIs to connect the control plane to different applications, network applications, for example, security, routing, traffic engineering, or others. These are our contributions in the paper. We propose an SDN-based IoT data path programming framework using EPBs, external processing boxes, we will see in the coming slides, that complements cloud computing by providing efficient routing and aggregate computation at the fog layer using SDN-compatible switches like OpenFlow, OVS. We define user requirements formally and design the programming syntax to incorporate these requirements into the framework. We devise an efficient data path computation algorithm that outputs network resource saving data path while satisfying each user requirements, for example, performing at aggregate computations or computing the delay, etc. This is our target network. We have presented a hierarchical view of the target network. So on the top, we have the cloud layer where the actual cloud of the server lies. Then we have the fog layer that consists of the SDN framework, the SDN controller, and the L3 switches. All of these L3 switches are embedded with a DPI engine as well, and each of these L3 switches are in turn connected to multiple base stations, and each of these base stations are then connected to the IoT layer, in which each of the base station is connected to a cluster of IoT sensors, from which the base station is collecting data and then forwarding that data to the cloud through one of the L3 switches. This is the overall architecture of Flip. It is mainly composed of 3 modules, as you can see in the diagram. The first module is the translation module. The second one is the SDN module, and the third one is the EPB, external processing box. The job of the translation module is to translate user requests and pass these translated outputs to the other 2 modules. The user can write requests to the translation module using the provided syntax we will see in the coming slides. This translation module communicates with the other 2 modules via RESTful APIs. The SDN module consists of an SDN controller, where we have some SDN applications running on top of it, which include the delay applications, the routing application, and an application to deal with the user requests. And then we have the open for compatible switches, the L3 switches. The EPB module consists of a Flask application framework that allows us to have RESTful communication with the translation module and write that data to a configuration file for later use by the DPI engine. So the DPI engine gets the instructions from the configuration file, and each of the DPI engine is connected to one of the L3 switches, and it starts processing the packets, inspecting the packets according to the given instructions. Our goal is to establish appropriate data paths for massive IoT data with efficient in-network data processing and routing while meeting various user requirements. For a clear understanding of the user requirements, we articulate the following user requirements. So these are the requirements that we have incorporated into Flip. The first one is computation. Computation is a crucial user requirement for in-network data processing to reduce IoT data packets, the number of IoT data packets, and relieve burden from the server cloud side. The next one is the delay. The delay requirement limits the maximum time taken from data sampling at base stations to user designated destinations. We will see in the coming slide. Then we have the coverage requirement. In many IoT scenarios, such as communication between hospitals in one or more regions or gathering sensory weather data from multiple sites, coverage is an important user requirement. Then we have the rate requirement. The rate requirement allows user to select the IoT data collection rate. For example, the base stations are publishing data at the rate of 100 milliseconds, but the user wants the data to be only received at the rate of 1 second. So they can set the rate requirement in the instruction and send it to the translation module. This slide provides an overview of how the delay application is working in Flip. So the user sends a request. It has some delay requirement. So we get the Steiner tree for this application, and it involves all the base stations and the sensor clusters involved in the communication. We compare the route from those clusters to the user with the given delay condition provided, and we notify the user if the delay condition can be met or not. In this slide, we show how the user command syntax that we have developed actually works. So for example, let's say the user wants to perform these operations on the selected base stations in the target network, as we saw in figure 1, in an aggregated manner. As you can see, we have some nested operations as well. So the syntax for this automated network setup is something like this. So we have the operations, sources, list, destination, and requirement arguments. So the operations can be minimum, maximum, calculating the sum, subtraction, or multiplication. The sources can be a set of source nodes, for example, the base stations like base station 1 to base station 10, and the list variable is a unique operand. It can take a simple variable like the source, or it can take in a new instruction in a nested way. So if we want to embed this instruction into the flip syntax, we can write something like this. Following the previous slide, a task graph can be made from the instruction that we saw in the previous slide, like this. This is done by the translation module, and this task graph is then mapped to the actual network of the figure 1 to assign DPI engines from the network graph to each operation in the task graph in an automated and distributed manner. So the heuristics for this mapping are presented in the coming slides, how these actions are actually mapped to the actual network. Once the heuristics map the operations to the DPI engines, a Steiner tree is created between the source node, destination, DPI engines and the destination, and the data is processed and sent. So this is the algorithm that we have developed to compute the efficient data path. So the components include the network topology, the subgroup of base stations that will actually be sending the data, a destination node, a server or a host, a tree that is actually the task graph that we saw in the previous slide that is describing the user requirements. So root will be the destination, leaf nodes are the base stations, and intermediate nodes will be the operation nodes. And M, this is the ultimate goal that we want to achieve, that is a set of switch nodes on which operation nodes are assigned. So this is the actual mapping. We would like to take the operations from the task graph and actually implement them on a set of switch nodes. So first of all, we would like to get the edge nodes, meaning the edge switches that are directly connected to the base stations. So starting from here until this point, what we are trying to do is we are trying to separate or collect the switches that are connected directly to the base stations. So we get that list of edge switches here in the connected switches. Then we start moving up the hierarchy. So we go to the parent node, and if the parent node is visited, so we break the loop. If not, we add it to the visited list and we start collecting the inter switches. So first we see the adjacent switches, if the parent switch has any adjacent switches to it or not. And once we finish that list, we move up the hierarchy. We move up to the next parent node and so on, and we keep going on in this loop. So at the end, we have a list of switches that include the edge switches that are directly connected to the base stations, and then the intermediate switches that are actually the parent nodes. And then we send all these values to the Steiner tree, and we get the efficient data path that we want and the switches on which we would like to perform the actual operations. So this is the experimental evaluation of a flip. We have used the simulation environment called Mininet, which is commonly used for SDN experiments. These are the experiment parameters that we have set, and this is a sample request subset that we have used, and this is the topology. These are the experimental results of flip. So we generated 40 random requests for each experiment, and for the baseline we have selected the cloud processing, in which all the base stations are sending data directly to the cloud. In figure 7a, we have compared the packet count on each switch for all the requests collectively. So how much packets are going through each switch for all the requests. So as you can see, as we move up the hierarchy, these are the children switches, and as we move up the hierarchy, these are the parent switches. As we move up, as you can see, the parent switches have the least number of packets going through them in case of flip, while in the case of baseline, as you can see, we move closer to the cloud, so this becomes the bottleneck. In figure 7b, the overall network traffic for each request is shown. So in this diagram, we show how much packets were generated for each request on all the switches in the overall network. So as you can see, the same almost similar trend as we see here. We have higher peaks in the baseline and very small peaks in flip. From the results of all the 40 requests, we observed that Flip has reduced the average network utilization by 45 to 77%. In this slide, we conclude our presentation. So Flip introduces efficient in-network processing of IoT data that reduces the amount of data arriving at the server or cloud. We show through experiments that Flip has the potential to reduce the bottleneck issues of handling IoT data at the server cloud while meeting various user requirements. Experimental results show that the overall network utilization is reduced by 45 to 77%. From these results, we conclude that Flip has the potential to be effectively used in large-scale IoT environments. That's it for our presentation. If anyone has any questions, they can reach out to us on our provided emails. Thank you everyone for your time. Have a good day.